Welcome back to the deep dive. Today we're looking at something pretty fundamental, the challenge of mapping a full 360-degree space.
Right, and not just taking a picture.
Not just a picture, but knowing the precise, measurable distance of every single point in that picture. We're getting into a paper on Depth Any Panoramas, or DAP.
And that's the word to focus on for you, the listener. Metric depth.
Yeah.
We aren't just guessing if something is near or far.
Mm-hmm.
We're talking about calculating the actual distance in meters.
So our mission today is to unpack how DAP manages to give these really dependable distance predictions that work across all kinds of different scenes, right? Indoor, outdoor, you name it.
Exactly. That's the holy grail here, generalization.
Okay, let's start at the foundation. The sources say DAP is built on DINOv3-Large as its backbone. Why that specific vision transformer?
Well, if you want a system that can handle literally any panorama, you need a starting point with incredible generalization.
So it's already smart.
It's already seen the world, you could say. DINOv3-Large is self-supervised, so it's already learned to categorize the visual world's complexity before it even learns a single thing about depth. That's what makes it so stable when it sees something totally new.
Okay, so that powerful backbone is step one. But here's what I'm wondering. If DINOv3 is so capable, why this whole complex data-in-the-loop thing? And this massive data set mixing synthetic and real images.
Yeah, you'd think a great backbone would mean you need less data, right?
Exactly.
It's about the quality of the ground truth. Getting perfect, reliable depth maps in the real world is it's incredibly difficult and expensive.
So you turn to synthetic data.
You have to. High-quality synthetic data from something like a UE5 simulator or even text-to-image models gives you flawless ground truth to learn from. It's really the only way to do this at scale.
But that leads directly to the problem we always talk about with synthetic data, that domain gap. A model trained on perfect, clean computer graphics.
It often falls apart.
Yeah, it falls apart when it sees the messy, unpredictable lighting and reflections of the real world. So how did they bridge that gap? This seems to be the real aha moment.
It is. This is the core innovation. They knew they couldn't just feed the model a bunch of random noisy images from the web.
So what did they do?
They built a three-stage pseudo-label curation pipeline. Think of it like a quality control system. They use an early version of their own model to guess the depth for all those unlabeled real-world photos.
Creating pseudo-labels.
Exactly. But then this pipeline kicks in. It's a high-tech filter that validates, refines, and curates those initial guesses. It turns messy web data into super reliable training input, and just like that, the domain gap starts to disappear.
So they fixed the data problem. Once the training data was solid, they moved on to the model architecture itself, optimizing it for consistency. What were the key additions there?
Three main things. First, scale. In a panorama, you've got a chair right here and a mountain way out there that can take up the same visual space.
So the model gets confused.
It can, yeah. So they added a plug-and-play range mask head. It's a special component that helps the model understand and weight distances properly so close objects don't just overwhelm the whole scene.
Smart. And then sharpness. Are they just focusing the model's attention on the hard parts, like edges?
Precisely. That's the sharpness-centric optimization. Depth maps usually fail right at object boundaries. This forces the model to get those edges right, where depth changes abruptly.
Okay, and the third piece?
Geometry-centric optimization. This is what ties it all together. It enforces consistency across the entire 360-degree view, making sure the final depth map actually makes geometric sense as a unified 3D space.
So after all that work on the data and the architecture, how did it actually perform in the wild?
The results were excellent. It did really well on the big benchmarks like Stanford2D3D and Matterport3D. But the crucial part was its zero-shot generalization.
Meaning it worked on data sets it had never ever seen before, with no extra training.
That's the one. And that's the real proof that this is a truly generalized solution.
So the key takeaway for you, our listener, is that DAP really does seem to merge the scale of synthetic data with the accuracy you need for the real world. It delivers these remarkably stable metric predictions.
Yep. They took a powerful backbone, used it to clean up messy real-world data, and then fine-tuned the architecture to handle the specific quirks of panoramic views. It's a genuine step change.
Which brings us to our final thought. If a system like this can now reliably map metric depth in 360 degrees, what does that immediately unlock for real-time applications? Think about autonomous navigation or maybe even building high-fidelity virtual environments on the fly. That's the question we'll leave you with.